So to do a few more examples with the alternating series test. Let's start with this one here. We see it's got the -1 to the n-1. So there's my alternating series test. My Bn here is going to be 1 over natural log of n plus 4. So, and we can sort of mentally see that this is going to go to 0. That should be fine as n goes to infinity. So let's do my first one. Bn plus 1 is going to be 1 over, right, natural log of n plus 5, right? But that is actually less than 1 over natural log of n plus 4, since natural log is an increasing function. So I can say natural log of n plus 5 is greater than natural log of n plus 4. And I can just write natural log as an increasing function. Now, if I wasn't clear on this, it's clear from the graph. So if you wrote that, I would absolutely accept that. But if you're not clear on whether it's an increasing function, you can always take the derivative and see that the derivative is positive, stuff like that, okay? Fine. By the way, just since I mentioned it, if it was, sometimes you do have to do that. If it's a very complicated function and you don't know what it looks like, you need to find out if it's decreasing and messing around with these inequalities isn't working out, then you can always take the derivative and check that the derivative is positive. But we'll mention that later. Again, so we did this, yes? So yes, Bn is decreasing. And the limit as n goes to infinity of Bn, which would be this limit, right? Now we know that as n goes to infinity, natural log of n also goes to infinity. So we have 1 over infinity. This guy is going to go to 0 as desired. So series converges by the alternating series test. Okay? Typically, where these alternating series tests are going to fail is in this here, if your limit isn't going to 0. If you can't get that the BNs are decreasing, maybe the test is going to fail for that, but then you can't really say anything about it. But typically for our examples, it's going to happen here. That doesn't mean you don't have to check this, right? Unless it diverges, then you don't have to check it. But you should be sort of expecting to always have to show that the BNs are decreasing, and that can be the more difficult even part of the test, because sometimes you have to do other things. All right, so that's a good time for me to talk about that, actually, because in our next example, I think we have to do that. So let me go ahead and talk about how to show Bn decrease. Okay. Obviously, you can just simply show it like we've done in the last 2 examples. You can do showing that Bn plus 1 is less than or equal to Bn. But you can also show slightly different ways. Bn plus 1 over Bn is less than or equal to 1. Right? That's always good. Sometimes good. This is actually, we're going to use this in my next example because it has an exponential. It has a 10 to the n. And when there's an exponential, like this ratio helps. You could also sometimes show bn plus 1 minus bn is less than or equal to 0. I'm sure that these are pretty much the same, very similar. Right? And the fourth thing you can do if all else fails is show that the derivative is positive. Show that bn, negative. Right, because we're trying to show that it's a decreasing function. So if a function is decreasing, its derivative is negative. So that's always a possibility. I listed it there last because it may be a last resort possibility, but you can always do it. Okay, so do keep those in mind as you go through these. So my next example is going to be this guy here. Okay, which we can use the alternating series test on this guy here. Okay, because it's an alternating series. Now, so I left these on the board. If you try to do this first one, you can. It's not obvious, right? Because n plus 1 is bigger than n, even though 10 to the n plus 1 is less than 10 to the n. If we take out, and you can do this. You can do this, but it's a little bit nicer, I think, to do it this way, because I don't like writing down an inequality when I don't know if the inequality is true. Right? So write it down and you start doing things, and God knows what's going to happen. So I like to sort of figure it out instead, and this, or you could do, but this one is kind of a nice way of doing that. So here our bn, again, is n over 10 to the n. And if I look at the ratio of bn plus 1 over bn, all right, yeah, it's not great at first because you have a compound fraction, but it's easy to get rid of it, or work it out rather. 10 to the n, and this is n times 10 to the n plus 1. Well, remember, 10 to the n plus 1, and I'm going to write this out because we maybe haven't seen it for a minute, but we'll be using this a lot in the next 2 weeks. This is just 10 to the n times 10. So the 10 to the n's cancel out. I have n plus 1 over 10n. All right, well, that is definitely less than 1. Right? So, yes, this shows that the bn is decreasing. Okay? Now, what about the limit? Okay, that's gonna go to 0 because this bottom goes up much faster than that one, but how do I really show that? I can use L'Hopital's rule. Technically, I have to change the n to an x. Now, if you don't do that on your test, I'm not going to hunt you down because I know what you know, I know what you mean. But this is what we have to do. Technically, we want to do L'Hopital's rule with an x so that we can actually do the derivative. Okay? And then this would be 10 to the x times natural log of 10. Okay? And then, of course, this is 0. So there you go. Thus, series converges. by this alternating